All right. Thank you. This is my first time introducing in the hybrid setting, so help me. I don't know who to address, you or the cameras. Anyways,
here because we can't see you.
I see. All right, there you go. Thank you. See, one of those iron those difficulties. Okay, so it's my pleasure to introduce to our digital and in-person audience here, Dr. Joon-Ho Choi, who is an associate professor of building science and also associate dean of research and creative work at the School of Architecture here at USC. Welcome to RSI. Prior to taking this position here and his PhD in building performance and diagnostics at Carnegie Mellon University, and worked as assistant professor in the Department of Civil and Architectural Environmental Engineering at Missouri University of Science and Technology. So Dr. Choi's primary interests include biosensing controls, human building integration, intelligent building systems, including systems integration, advanced control systems, and environmental sustainability, which are all very important topics. So we look forward to hearing from you. Thanks.
Great. Thank you very much. Thank you for a great introduction, Christina. And thank you for all the setting up very successfully, Yolanda and Christina and Arma. So I think I joined the USC School of Architecture 2012. So yeah, and since then I have many opportunities to talk to hear about the reputation of ISIs, but unfortunately, it took for me to wait 11 years to stand over here. So I think it is very meaningful, very honorable for me to talk to you today. So since I joined USC, so I developed the research theme, so human building integrations, because these days modern people spend their 90% of their time, more than 90% of their time indoor. So that's why the importance of indoor environmental quality, thermal, acoustic, air, and some lighting is a really key important for your physiological health and work productivity. So today I'd like to share some of my recent work and background, as well as some what I am interested to work with ISC, the colleague and partner, the collaborators. So yes, this is just a brief background. And before I joined USC, I used to work at the University of Missouri-Rolla, so they changed the name recently. It is in the middle of nowhere. No Starbucks, no ice cream shop, only one Walmart. That's it. So on 25,000 people in the community. So there's only one coffee shop at the time. So recently I heard that 2 Starbucks opened, but and also during the career, because I'm originally from South Korea, so I had to serve in military for 2 years. So it gave me a lot of some opportunity to train myself for physical strength as well as some organizing skills. So how to work with some other people in a mutual way, and also kind of one single way communication mode. So, but that experience give me a lot of tough season, but also give me a lot of the moment to develop my skill to work together with other people. So actually, very fortunately, I used to work as an intern when I was a graduate student in a general hospital. So at the time, not as a patient, I enjoyed going to that facility as an intern student. And then I was able to meet a lot of patients who are physically limited. So unfortunately, but especially ICU, intensive care unit, the left one and right one is a general hospital, general patient room. So those patients frequently, and I was able to see the many cases, the patients their physical condition is very limited. So that's why only thing they can do all day is just sitting just lay down in a bed and seeing some very bright fluorescent light all day long. So, and the other one is that their temperature, lighting, everything is 100% controlled based on the preference of a doctor and nurse, not the patient. So it gave me a lot of inspiration and also motivation. Hey, what should I do to further in the architecture domain to make the people healthy and comfortable and then stay in a well-being. And this is one commercial building in Northern California. So it was built in 1980s. So 1980s, so it is not much common to have some sustainable design, environmental design to accommodate in a building project. But this one is really innovative, relatively, considering the 1980s era. So they adopt some slope loop, and then they also adopt the light shelf. So it means that they can accept the daylight the more that in an inner space. It means that they can minimize the use of electric light so that they can save energy. So by maximally using some daylight. So this is really a nice view from the lobby. So they also have a skylight so that they can spread out all the beautiful daylight across the space. The thing is that people started using umbrella here and there, rainbow and orange, those things, and then blue. That is my favorite color. It happened because maybe, as you guess, too much light. And this is a public library in China, and then this even is designed by a very, very famous architect, Renzo Piano. So this is public library and all the glass covered, so it looks really nice. But people start using umbrella again, so in a different way. So like this. So this guy very looks serious, and only except this guy, almost everybody using the umbrella like this way because too much light. So so I believe that as far as you visit some commercial office building, you may find that this very clumsy looking like a box, plastic box, with a thermostat, because nobody in a facility department wants to use you guys to access and control the light. So that's why they put some box like this. But the people are smart, so they are attacked with ice to cool down the temperature so that it can actuate the heater, or you can pick with some sharp like a key to push the button. Okay, that happened. 21st century, very innovative. I'm not sure it is smart, but very innovative. So wherever you staying in a residential, office, healthcare, and school, we are always surrounded by thermal, acoustic, air, and lighting, which is a visual quality. So the issue is that the building occupants demand very different thermal, lighting, acoustic, and air condition, depending on their physical characteristics. But unfortunately, the building performance standard says that, hey, 75 degrees Fahrenheit should be happy to everybody, okay, to follow that, set everything 75, okay? Even though I prefer 78, and some people may prefer 73, it is not possible. So everything these days is smart, right? Smartphone and smart car, smart TV, smart home, smart city, smart beer. Can you guess what is smart beer? Yeah, it comes with a very smart sticker, show that right temperature to drink. So kind of change color. So the thing is that, in the US, the commercial building, so we are paying for the administrator. So this is based on administrator. So their annual salary, average salary is $45,000 per year. And for building operation like this, so we are spending $450 per person for utility. So utility means that heating, cooling, ventilation, lighting, so and also plug load like these appliances. So the thing is that if we can increase some worker productivity by 1% per year, we can make a extra revenue, so profit for $450. That 1% increase the worker productivity can cancel out the utility bill. Right, so that is really important to some financial, logistics, because that the worker productivity, even though it is not much tangible, but as far as we can provide healthy indoor environment quality and comfortable environment condition, their worker productivity could be enhanced, and then so that we can save a lot of financial resources, while we can also cancel out such as utility bill financially. So indoor environment quality, so they accommodate those 5 major components. So those major individual environment quality components affect the overall IQ condition in the building, and then it can contribute enhancing worker productivity, health, and also environmental benefit. And so the thing is that human-centered approach is quite some challenge these days. So smart city building system, smart environment control. So many things we set up by with the help of an electrical engineer or computer engineer. But the thing is that they make a perfect hardware setting, software setting, but we frequently forget the user, right? The city building system control, the indoor environmental space, it's basically for human, but there is no human itself. There is no occupant itself, okay, user itself. So that is very unfortunate condition. So in a conventional theory, for example, thermal comfort. The reason why I think thermal comfort first is that for building energy use wise, so 45% of building energy is spent for heating, cooling, ventilation. So that is a significant amount of high portion of building energy. So this is thermal comfort theory, according to building standard. So the formula care clothing and activity levels, like learning, sleeping, and sitting. And then the environmental factor, temperature, humidity, and radiant temperature, like a cold surface, warm surface, and air velocity. Okay, so those are conventional parameters. So the thing is that when we have some heat balance between the ambient and your body core temperature itself, so we say comfortable condition. If it is cold, we are losing losing temperature energy to outside, cold. If we hot air, we gain heat, that is warm air, the warm condition. But the thing is that the conventional standard, they don't care about body mass index, gender, age, ethnic origin, and other individual factors. So BMI, as you know, higher BMI, according to BMI index, I'm highly obese. So because of too much fat over here. And then my wife is weight-wise almost half of my weight. So we are always fighting. So especially during the winter like this season, she always said that, hey, I need to increase the thermostat temperature. And I insist that, hey, I prefer the lower temperature. So there are a lot of huge gaps. So that's why we fight. So the thing is that according to my friend who is a medical doctor, the insulation over here, the fat layer is basically good insulation material. So it can protect my core fit, core temperature, so that I can protect myself from thermal stress, which is cold drift. So in terms of that, I'm very proud of myself because my fat layer to contribute environmental sustainability and some energy conservation by getting a lower temperature setting in the winter season. Anyhow, so that is the one. And the funny thing is that many good universities like Berkeley and some university in Denmark, Technical University of Denmark, they're using the human mannequin for thermal study. But the thing is that I know that her name is Jessica, so I saw that when I visited their facility. So they are using kind of mannequin which is too much averaged. So they don't care about skinny person. They don't care about like a big person. It is more like an average mannequin. So it has heartbeat. It has all the blood vessels. It's a quite expensive toy. So for some research purpose, the issue is that they don't accommodate any extreme condition in reality. So, but the other hand, the human body itself is a kind of well-integrated sensor. So this is the data that I collected from many building facilities in the US. So this indicate some building, and this plot indicate measure the temperature from individual workstation. So you see that the heating over here, cooling season. So this is basically summer. So the temperature is supposed to be within this range for kind of comfortable comfort defined by the standard. But you see that some temperature is really lower than the recommended range. So these are basically 72.3 or 60 something over here. So the issue is that in the US, we are spending too much energy to overcooling while we are frequently compromising users' environmental satisfaction and also the energy efficiency. So that's why the common issue in a building is that too cold during the summer and too warm during the winter. So that is a very ironical situation in the US. So let me share some videos. This is basically from commercial. But let me share maybe 30, 40-second things. But it just show very good real reality.
Oh, hey, hi, Stacy. How's it going?
Really? It's 83 degrees outside.
Right.
And look at me.
I know.
Yeah.
But it's been just so crazy slammed.
Todd, you've got to do something about this office. You could bake a chicken in there.
Right. I'm gonna take care of it for you, okay?
Good man.
You bet.
Okay, anyone else?
Carry on, folks.
Yeah, I think this one is very summarized.
That's ISI.
Yeah,
Yeah,
that's
yeah.
this building.
Is it? Okay. Oh, I was about to say that. It might not happen in this building, but it is not. So actually, this is a commercial from the phone-based environmental control the company. So they developed some apps so that you can report, oh, I'm in some room number ABC, and then I'm a bit cold, and some people may say I'm hot, and then they collect all your vote and then provide some temperature. So it's still averaging process. So the other one is that when this one is quite a bit 7 years old item, actually product wise. So the thing is that even though the smartphone app, many people believe, oh, it work, but it is not actually. So about maybe the thing is that after 2 weeks and 3 weeks, so before 2 to 3 weeks, at the beginning, people are excited. Hey, I have such some smartphone app, or really intelligent, blah blah blah. And then I just vote frequently. But after 2 weeks or 3 weeks, nobody cares because you don't want to be distracted by this weird remote control, so voting system. So that's why the people's use rate is really decreasing like this way significantly. The good thing is that the people say that, hey, I'm happy, I'm willing to wear many good devices as far as it provides some health benefit, work productivity benefit, and more also reporting by health condition. So we are really good time. It is a really good timing because with the help of such as some advanced technology, it is really easy to collect the data as compared to the past. And the other one is that even though we check the body temperature for COVID symptom or any fever symptom, but basically we have two temperature. One is body core temperature and the other one is body skin temperature. So core temperature should be maintained in a certain level, almost 100 degrees Fahrenheit, but the skin temperature is always fluctuating to maintain your thermal physics. Okay, so between ambient and your body. So in a sweating, when you're staying in a very warm condition, very cold condition, shivering, but between these two extremes, skin temperature contribute to protect your body core temperature. So it means that it can tell us many good information. So based on the physiological principle, we developed biosensing adaptive environmental control. So as a function of human physiological information, like a skin temperature and heart rate variability. So as far as we provide that information, and this thermostat has a capability to estimate the individual thermal comfort and thermal sensation, so too cold, too hot, or moderately cool, moderately hot, and then override temperature so that it can stay in a very stable condition in a working space. So this is the mode. The reason I select 10 body segment is that because depending on your body segment, your skin temperature provides completely different level of skin temperature. So that's why I explore which body segment is generate most meaningful data to estimate users' environmental satisfaction, thermal sensation. So this is the selected body segment for the research. And then, this is a human subject A 2 through 16. As you see that even though they are staying in the same thermal condition, their arm temperature condition is completely different by individuals. And then also even a single person, their arm temperature, forehead, wrist, and front and back, their temperature is completely different. It's not surprising, but it is the fact. And also depending on gender, so they have clearly different some differences like this way. Yeah, this one is more like a sensation, thermal sensation, slightly cold, neutral, slightly warm, warm, very warm. Okay. And then we have also the cold and very cold condition, but our chamber cannot generate such as some cold temperature. So, and the body mass index. So we grouped so lower body mass index and then higher BMI group and compare what's the difference when they report the same thermal sensation. So it's not surprising because the individual level, even there are a lot of variations. So even grouping by BMI, gender, definitely it is obvious to see the large difference. So with the help of a machine learning algorithm, so we started investigating how to estimate the thermal sensation as a function of skin temperature. So this is a one, and then we are using some absolute level of skin temperature, and then by training and some for testing, so data. And then we found that when we accommodate more sensing point, like a waist, arm, wrist, and front, forehead, like neck, we can accomplish almost the highest some accuracy rate. Okay, but when you select only one waist, only 76%, 70 or 68, so very, very moderately low.
The task here is predicting the 5-point thermal sensation rating.
Yes, right. Yeah, actually 7 point, but we don't have any, too extreme condition. So the thing is that so more sensing point guaranteed higher accuracy, but nobody wants to wear a sensor like this way, right? So yeah, it is very crazy. So that's why we want to change. We want to select some optimal body segment by minimum sensing point, so that we can for practical purpose. So we are using we use the gradient and skin temperature, and then do it again, and then we found that wrist, front, and back, like over here, the measured temperature provide 94% accuracy. So which is quite good. So and then we made some confusion metrics like this way, and then which sensation is more easy to predict like that. So this is a result. And then we validate this control, the prediction model, so in a real office building downtown Los Angeles. So it was quite interesting, and then we were able to see that some 94%, 95% accuracy rate in a real setting. So this is the algorithm that we developed, and this is the algorithm, conventional algorithm for HVAC system. So most frequently it is missing. So we try to integrate, so we can control even window mount of the AC, very cheap one. So as far as we can provide some intelligence, we can operate such as some cooling system or heating system in a residential level without spending much budget. So, and the other one is that in an open office. So as far as we provide some individual grill like this way, so we can generate a certain level of warmer and certain level of cooler temperature condition in each cell. So that is one thing. And also the PEM, so personal environmental module, is commercially available. So it is actually got some main air from the duct, main duct like this. And this, in this case, like a floor access underfloor air system. So we can reconditioning, so like a recooling, reheating, and provide conditioned air to the user, like a car dashboard. Okay, so they're design wise. So that is some one place that we can plug it in. Okay. So I started hearing some kind of complaint from the people. Hey, I don't want to wear any devices on my body. So what can you do? And that gave me a lot of some inspiration. Oh, what should I do? And then we started using the infrared sensor, because infrared sensor, when you use that, it's much easier to detect your, even remote sensor can detect your skin temperature. But in that case, your face is always like the very just bare skin, so it is much easier to detect the user's skin temperature from the face. So we measured the skin temperature and to see that if it is possible or not. So we found that depending on the body point on even face, they generate a different level of skin temperature. So we try to find that which body segment, body area, skin area is more meaningful or less meaningful. So this is the temperature variation. So we select some 5 points. So cheek and left and right, and chin and forehead left and right. So those are points that we measured, and then we found that their temperature always fluctuating. So even in the same thermal condition, their facial skin temperature is very different depending on the spot. So we found that, okay, so in that case, we may use some overall temperature instead of just picking one specific point from the skin. And then we made some decision tree, very simplified decision tree, so that we can, based on the use, develop some general model. So we can estimate, we can develop this one like this. So like the model-wise, like a gender, the male, and skin temperature, overall facial skin temperature is less than 30.7 degrees Celsius, and gradient is larger than 0.02. Ambient temperature is 26.3 or less, and then neutral. It means that the system-wise, no additional cooling, no additional heating, just stay in the same temperature. So by doing that, we can make some real-time sensing and real-time control in an individual setting. And then we also find that using some neural net, and the accuracy rate, overall accuracy rate is 94%. So that is the highest that we reached. Okay. And then another one is that for the next step, okay, for the thermal study, we understand that each body segment is more meaningful. Yes.
Quick question. Why are you measuring accuracy, like performance as accuracy rather than error, means MSE, mean squared error?
Oh, yes. Actually, we have some, but yeah, the thing is that we estimate the thermal sensation, so which is basically 7-point scale, but considering that's a real reality, so we just reduce the 5-point scale. So so the 5-point scale, that is the one that we adopt.
Oh, okay, so you're not predicting temperature. You're
Right, no, not
predicting,
temperature. Yes.
Okay, I see.
Yeah.
Okay.
So for the next step, because of the as a next target in a building performance, a building system, so the lighting consume 20% or higher energy of total energy in a building usage. So we select that, hey, how can we control the lighting using some human information? So lighting quality is really important because you may have some visual acuity issue, and then you have some tiresome on your eyes very instantly, because the temperature, if I turn on heater, it'll take time, we call it time lag, to affect that corner temperature. But the lighting is very instant, right? It's just a dim up and dim down. We can expose the change of temperature. So based on the same, the similar platform that we collect the lighting condition, what the actual lighting conditions are in a commercial office building. So this is the building, so in the US, here and there, San Francisco, DC, Arizona, Texas, and then we collect the individual workstations lighting level, okay? So in an office setting, 500 lux or higher is recommended, but in reality, some people use 400 or 300, even almost zero level. I think this guy is in cave or something. And then over here, this guy maybe uses 1400 lux. He's almost 3 times higher than recommended range. So means that people need some different lighting level for their task, okay? Paper-based task or computer-based task, or any drawing work, something like that. So the other thing is that once you reach almost 40, your visual acuity is going down, going down, going down. It means that maybe 20 or younger people need this level of lighting for reading. The people within this range, they need this much lighting level. Okay, that is the overall average at the trend. And the other one is glare. Okay, so we are exposed to glare, especially in your workstation. You're not supposed to, your vision field, your vision field is not supposed to accommodate lighting source. So I can see you guys, but in my vision field, I can still see the lighting source from ceiling. So in that case, you have a lot of some fatigue and the glare. So if you see me, so from your workstation, you can also see very naturally, you can also see that this lighting source. But if you do this way, can you do this way? Okay, what do you feel? very comfortable, right? Your eye. So that's why we need to be very careful to avoid the glare. So otherwise, because it is not easy for just the normal people to recognize any glare in their workstation. So that's why in some case, you in the morning after coffee, you start working very joyfully, but maybe 1 hour, 2 hours later, you start looking like this way. So you try to reduce the size of your eyes because it's too much light on your eye. Okay, so if we have such a condition in your workstation, my recommendation is just wear a baseball cap. Okay, so it is much easier for you. So anyway, so it happened. So we have some tool how to detect some and how to detect what the glare sources are and how much the glare source is available in your workstation, stuff like this. And the other one is that your task field and your background field need to meet a kind of certain rate of contrast ratio. So brightness ratio, so somebody call it. And so based on that, so I started studying that, hey, if we can understand what the eye information, so we can connect with some lighting parameter, so lux, kind of some illuminance level, lighting temperature. So this is a 6,000 Kelvin, 6,000 Kelvin incandescent lamp. That is 2,500 Kelvin. So that is color actually, but we call it color temperature. And contrast ratio, as I said, that's the background and task, and the text type, computer and versus the paper. So as far as we understand those relationships, so we can accommodate that algorithm for lighting control or glare control in the workplace, for example. So at the beginning of the research, I thought that, hey, everybody has an eye looks like this. Okay, so beautiful round shaped eye. So that was a thing. So it is much easier to use detect the size because if you went to really good high school, you still may remember higher scale to estimate the size. Okay, so I thought that it is common and very easy to estimate, but in reality, alien shape. Okay, so broken shape, and it is also broken triangle. Okay, so I have one image for me. So actually, so I also my eye is not clear enough, not clear round shape enough. So we start using, instead of just this formula, so we start using some pixel to estimate the size of your eye pupils. So in our test chamber, so by generating different level of lighting condition and the lighting color temperature, we did a lot of user study. And then, yeah, this is some samples, images that they collected that we took during the study with a student participant. And this is some interesting data. So illuminance level, and then this is sensation. So brighter and darker, okay? So that is a visual sensation. And overall, like this way, so from about 25 people. So people say that, hey, in a higher illuminance, people say bright. Lower illuminance, dark. Very obvious. So the same data, but I changed instead of illuminance, I use a pupil size like this. Okay. So in a very bright condition, definitely your eye pupil shrinked, right? So that's why their size over here. It is dark over here. But you see that maybe if you draw confidence interval, not good enough, right? So I found that, hey, depending on people, their actual pupil size is very different. Some people basically very large and some other people basically very small. So that's why we use some standardized or normalized process per person's data. So not like a group data. So this is the one. And we process some formula to that so that we can get some more segregation in terms of size so that we can easily tell the difference between the different sensations. Okay, so that is the one, so that we can estimate, oh, within this range, this guy seems to be neutral. Within this range, this guy seems to be slightly bright or slightly dark. So that work was invited to US Federal Science Engineering Festival, so a few years ago. And then we developed some prototype model over here, and then some portion of the research was reported in some newspaper and some video channel. And we developed some 2 prototype models. So this is a first one, second one, and this is more like a advertising video, so made by one of my students. And we target elementary school, and the other one is office. So over here, there's some model, like a survey, like what is your ethnic origin, what is your eyes color, and what is your age, and female, male, that kind of survey. And then we collected some training data set during the regular hours, supposed to be regular hour. And then we measure the lighting level, and then we measure the eye pupil size like this way. And then there are 2 light bulbs. So one is controlled based on the use of the eye pupil, and the other one is by my hand. So I turn off intentionally. And then it's a very primitive prototype. So it is the dim up to compensate. So I increase the lighting level in the maximum level, and it becomes darker like this. Okay, so that was the first prototype model. And then for this one, because to generate more real, to mimic the more real workplace situation, so we control the more number of light bulb, and then different light color temperature.
Question. So my understanding was that what you had done is that you had a relative measure of pupil size in order. So how long does it take to establish what that relative measure is? It in this it looked like maybe 30 seconds, but
No, it's just like a simple sample image. So usually we at least we collect the data 6 hours or 4 hours, 6 hours. So that is for the collection period.
I see.
Okay, so
I have another question came in line from Pat Langley. So thank you for talking not about the learning algorithms, but rather about how you formulated the problem and collected this data, which are more important to real applications than induction models. Another important topic is user adoption. Did you evaluate your systems in those terms?
I actually so this was a very short one, so 1.5 year period. So we were not able to reach that level. So I think there are some. To be honest, there are some limitations. So actually, how can you override during your workstation work? The thing is that this setting is based on the computer-based work. But when you read some paper or some article, which is paper-based reading, so in that case, you need some different setting. So yeah, so that is a kind of a limitation for that.
Challenging.
Yeah. And then, so yeah, from those work, I found that, hey, our human body to generate a lot of information. So only thing we need to do is to analyze them to estimate the user's need and provide that building service, so in the right time. And the other one is that these days, advanced sensing technology is available. So it is a really good opportunity for us. Even like infrared sensor, when I did the infrared sensor to detect the facial skin temperature, these days there are many like a laptop-based some camera have some function by using some filter. So I think that is also very available. So, and the other one is that obviously sensing frequency and then some duration. So that is always a kind of provides some limitation, and the size of a data set per user is also provides some limitation. So one thing that I think that we need to collect data for a sufficient training so that we can provide more optimal solution per user. So that is some lesson. So actually during the project, those things, because in our domain, energy saving is really important. Net zero energy building, carbon emission, zero emission, that is a really key parameter. But the thing is that according to Google Trend, people's interest is going down in terms of energy saving. So since 2004, during the Obama period is a peak by going down, going down, going down, going down. Okay, so, and the other one is people wellness. So wellness become like increasing their interest rate. So based on that, and also the energy saving strategy, there are so many strategies available in the market. So that's why I developed recently, so about 1.5 years ago, we established as a research center. So Center for Wellness in the Built Environment, so that we can we can do some research about human wellness and healthy indoor environmental quality and the sustainable design, smart connected community, and the environmental resilience. So I believe that that will be some good place for interdisciplinary research by accommodating my many other partners and collaborators. So we so that is the goal and then of the center. And we frequently have some meeting and also research seminar, and we invite some people for keynote the seminar talk like this. And then we also invite some people from the industry, government, and foundation and community, so that we can develop kind of a consortium group. Okay, so that those people can support our center while we are sharing some finding and some ideas with other people. So we invite about currently we have a member from the major architecture, engineering, or architect firm, and then most people are vice principal, and president, vice president, and then program manager and department manager. So we try to have more people so that we can have them be interested and to support. Based on their support, we can develop the more aggressive research work. So yeah, we recently have some consortium meeting. So second consortium meeting in October, and it was quite successful. And then some of the work was sponsored by those organizations, and those are kind of some my major collaborators to support the research. So actually, the many work has been recognized in good places, like the best paper award, those things. And I already tried to share the credit with my student, the graduate student, even undergraduate student, so that they can get some idea, get some credit, so that they can make a record on their CV for successful career development and job hunting. And so the good thing is that I try to share such an idea with the student as much as possible. So I very fortunately selected for the USSC Mentorship Award, so last semester. So that happened, but even though I was not able to attend the award ceremony, which is supposed to be very luxurious. Okay, so the one thing that I found during my research, I found that hey, privacy is really important. So I don't have any expertise in privacy. So privacy is something that we need to figure it out. And then for training amount of data set, we need to optimize or some getting, even though it is small, but we can extract, you should extract more informations. And so amount of data is a kind of issue. And individual versus a general model. So as I said that before, general model is more like more lump sum, but the individual model is more complicated, but more practical and more accurate. So, but the effort to make an individual model could be relatively larger than general model. So that is one thing we need to figure it out as a function of data set or some processing effort. And various environmental conditions means that even though I developed something for this building, this room, but when you're staying in a smaller room or larger room, or some different partners or different neighbor worker, in that case, you may have a different physical parameter, and also the air velocity for room and their layout of the duct is almost different. So that's why how to customize such a model without significant additional effort. And also how to differentiate the prediction target while using the same data resources. That means that, okay, so this is the most biosignal that I'm using for my study. But some data can be used for thermal comfort study, acoustic, visual, air quality, spatial, and psychological perception over stress and work productivity. So the thing is that we are still using the same data set to predict the different environmental parameters. So and also we have a different office layout, different building typologies: office, school, residential, healthcare, and commercial. So depending on typology, we need some different model to provide the best solution. So that's why I believe that the context-aware environmental control, in the built environment is the something for the future work that we need to figure out. So I believe that to accomplish this goal, I believe that the machine learning or algorithm artificial intelligence algorithm is a kind of must to figure out. And also, even though we have a lot of some variations, a lot of number of some different algorithms, but I believe that the context aware, some AI or context aware machine learning could be one thing that we can figure it out together in terms of, especially in the domain of building. So what I can offer if I work as an opportunity to work together with you, so I can be some bridge builder. So I have worked as an associate dean for research for 4 years. This is my 4th year. And then I believe that myself has a less communication barrier in terms of intellectual merit. So between with some medical school and then engineering or computer science, even don't science. So I believe that I have myself is well trained to communicate with those people and how. So, and that one, and also as a dean, associate dean, and also center director. So I am actively establishing the new initiatives, especially for research, by exploiting maximally utilizing the current intellectual resources available at ISI and also USC architecture. So I always like to work as a team, so rather than individual. So I think myself is a kind of have some skill to manage some collaboration or in the partnership. So for now, I'm working on I'm currently planning a consortium-based research center, could be off campus, and then smart technology-oriented research center research is quite important because that. Let me share this one. This is a smart building technology industry annual growth rate. So on average, so we are estimating 22% increase in every year. So it means that many people are very interested and there are a lot of opportunity to fill in with our research some outcome. And also, so I'm very interested in some consortium-based research center. So once we developed, so we are expecting to hire 10 PhD or postdoc scholars as a minimum. So I can definitely share some portion of those high recruitment opportunity with ISI. So, and also I'm currently making an effort to propose a new course in the school of architecture because artificial intelligence is a completely new thing, new novel item in our architecture school. So that's why I'm currently proposing artificial intelligence in the architecture context so that we can develop some idea to develop some creative design as a function of artificial intelligence. So as I mentioned, so I developed the human building integration so as a research theme, but there are a lot of key parameters of research and there are a lot of research gaps we can find. So I hope we can have an opportunity to work together so that we can fill out all the gaps through the collaboration. Yeah, thank you very much.
All right, thank you. We have one more. Maybe you can start with questions online. Excuse me. From the same person, Pat Language said, could you adapt techniques from recommender systems to infer personalized models from users to give them better building experiences?
Right. So yes, because it is based on the use of some AI functions, so ML machine learning functions. So once the system get used to the specific users, their behavior pattern and their some control pattern, so it becomes definitely smarter. So the thing is that one concern, practical and very popular concern, a frequent concern is that even though you might have 75 degrees Fahrenheit, for example, depending on season, depending on the climate condition, your 75 may not be a good one anymore. Okay, so that's why we need to accommodate some external data, which is climate data and weather data in real time. These days, it's very easy to collect the information. so that we can develop a more sophisticated model, so to provide or even suggest, because of your setting could be based on the historical data, but it could be different depending on some external condition or some internal condition. So that's why we need to be carefully read some context, so weather context, climate context, the season, time of day, and day of week, so that we can provide more better services. Yeah.
I mean, I imagine you get this question all the time, but there's been this giant shift in the last few years that many more people are working from home. Occupancy rates have sort of dropped, and
Right.
perhaps people are investing less in commercial space and more perhaps in kind of residential space. So how do you think that squares with, you were showing this forecast, there's a great interest in smart building, but perhaps less demand for new commercial real estate. How do you think it's all going to play out? Do you think
Right,
it's going to be more retrofit or?
Yeah, actually, one of our some current project is based on the hot desking system. So these days, the many organization or some company, they try to reduce their real estate size so that they don't need to waste any some space. So these days, as you may know, so for example, one of our industry partner, so I'm using their facility as a test bed. So they have a kind of login system, so you can reserve some specific spot and working in the workstation and go home. Next day you can select another one. So it's like a public library workstation. So the thing is that I found that I'm not talking about hardware. So hardware is more like based on the conventional facility managing the management. So but we are talking about like a data, sorry. So I think we can use it maybe cloud system or some disk system so that we can plug in any hardware so that we can generate some similar or some comfortable environmental condition, regardless of your some space, regardless of your physical location. So I think, there are so many people who are working remotely at home. So I think we can also make some platform to plug in in a residential, even though the data might be from somewhere else. So that is one thing that we can figure it out. Yeah. Does it answer?
Yeah, those are two great answers.
Okay, thanks. Yeah.
You didn't talk very much about productivity. You focused on wellness, right?
Right.
And so as important as wellness is, and I can see lots of possibilities here, if I come to work and my stomach feels a little bit off, I may be colder, I may be welcoming some other environment. I see lots of possibilities, but for, the performance that I have when I'm not comfortable, or when maybe things that I don't necessarily realize, right? That there's too much light and I'm reading much more slowly. So is that an important factor? Is that something you've studied? It would make it very compelling, right?
Right. So yeah, very good questions like that. And actually, currently I submit a proposal to NSF based on the collaboration with the ergonomics in industrial engineering. So because they are talk about worker productivity, and we are also talk about productivity, but there are a lot of huge gaps. So I found that in the industrial engineering, let me share this screen. So in industrial engineering, they don't care about lighting. They don't care about temperature. They don't care about air quality, acoustics. They assume that they're kind of acceptable. And then they start talking about task types, very detailed, like a kind of plant condition or office condition or drawing condition, surgery condition. So they completely different, talking worker productivity, but completely different content. In our field, very simplified. Okay, computer-based task, paper-based task, that's it. And then we forget any other things. But we care about temperature, lighting, acoustic, those things. So we found that there was a huge gap to estimate. So actually the worker productivity, so for now, to be honest, we assume that as far as we provide healthy indoor environmental quality, it will affect their productivity in a good way. But that is very primitive and very limited. So that's why we try to investigate the more detailed per task type, per environmental condition. So seamlessly between the collaboration, based on the collaboration. Yeah. So for now, we estimate the worker productivity. So based on, I think, a few hundred case studies, and we estimate that, for example, when you provide some overrideable smart in the like a user-friendly comfort temperature control system, it can guarantee approximately 5% productivity. So it can provide about 2,000 or 3,000 financial benefit. And then shows some first cost increase for remote control is $800 per workstation. So kind of some return on investment is about 200%, something like that. So that is the level of condition that we are talking of regarding work productivity.
Any other questions?
I have one last. So, I mean, have you thought about specifically sustainability in relation to these? For example, I have an office facing west. When the sun goes down in the afternoon, my office gets very hot. But if you have to cool my office and I'm going to leave in 2 hours, it's a waste of energy. So how do you square some of these sustainability goals versus comfort? And what do you think is?
So I think for that condition, the very simple $10 amount, maybe occupancy sensor can easily figure it out depending on the occupancy condition. So you can turn off and turn on. So that is one thing. But if we need to squeeze out more energy efficiency, because as I mentioned earlier, almost 60 or 70% of people complain too cold during the summer and too hot during the winter. So in the US, unfortunately, many buildings we are wasting such as resources with compromising the individual comfort. So I think there are many ways to aiming for the energy mitigation or energy efficiency. So we can cut out we can save those portion first, and then by optimizing the thermal condition, we can squeeze out the more energy efficiency. To accomplish more net zero.
Right. Yeah, and I agree that there's already a lot of inefficiency and we should reduce that. But I guess from a utility and that sustainability ethics perspective, do you have a stance or do you have research on saying here's when we can sacrifice comfort for a sustainability goal? Is there any kind of work that you're familiar with?
Yeah, baseline is that without with compromising the save energy with compromising individual comfort, we do not accept that one, because for now we prefer to spend more energy if we need to provide more comfortable service. So how to make up that one? We can use power generation. So because of the PV panel, for example, their conversion efficiency is going up these days. So it used to be 15%, these days 22%, and these days the better one is 25-6%. So even in Silicon Valley, one of company, they already developed a 50-something% conversion efficiency. So I think we assume that a bit biased, but we assume that within 10 years or 15 years, energy could be free. So by having such a some well-advanced some PV panel, for example. Yeah.
Well, let's thank the speaker and thank you also. All right.
Thank you.
Thank you.